In this video, we're going to look at properties of power series. We're going to combine power series by addition and subtraction. We're going to create a new power series by multiplication of a power of a variable or a constant, or by substitution. We're going to multiply two power series together, and we're going to differentiate and integrate power series term by term. The reason we're going to do this is we're going to be able to find power series representations for certain elementary functions by writing those functions in terms of functions with known power series, and we're going to be able to create power series that allows us to define new functions that cannot be written in terms of elementary functions. This capability is particularly useful for solving differential equations for which there is no solution in terms of elementary functions. So we have our first theorem here, which is combining power series. Suppose that two power series where I have both starting at n equals 0, c sub n x to the n and d sub n x to the n converge to the functions f and g respectively on a common interval, then the power series of the addition of this converges to f plus or minus g on I if this is a plus or minus. Furthermore, for any integer m greater than 0, any real number b, the power series b x to the m c n x to the n converges to b times x to the m f of x on I. And for any integer m greater than 0, for any real number b, the series of n equals 0 to infinity of c sub n b x to the m n converges to f of b x to the m for all x, such that b x to the m is in the I being the interval. So we want to find the interval of convergence for each of the power series, and then find the interval of convergence for s of x plus c of x when b is given as the summation of n equals 0 to infinity of 4 to the n, x to the n, 2 to the n n factorial squared over 2 to the n raised to the 2n. And s sub x is equal to n equals 0 to infinity of 2 to the n, or excuse me, x to the n over 2 to the n n factorial squared over 2 to the n, 2n raised to the 2n. And of course, here's my c. Here we go. So I'm not going to go through finding the radius of convergence because we did that in our last video, but I do know the radius of convergence for s of x is equal to e squared. And my c convergence, a radius of convergence for c of x, is equal to 10. So then the radius of convergence for s plus s, s of x plus c of x, well, if s of x starts at negative e squared and goes to e squared around some a being my center, and we're going to assume for right now they're non-inclusive. If my c of x, same center, goes to negative 10 and positive 10, then by the theorem above, the sum of these will be where these two intervals overlap. And the intervals in which they overlap is from negative e to e. Oh, excuse me, negative e squared to e squared. So that's my answer. By the theorem up above, basically you look to find out where the radius of convergence is. You look at where their center is, then you find their interval. And then wherever they both have that shared interval is going to be your solution. We also know from yesterday's, or 6.1, as your series gets larger, the interval gets smaller and vice versa. So as my interval, or as my series gets smaller, my interval gets larger. So there is the first example. If we're asked to find the radius of convergence for this rational function, The first thing we're going to do is break it up with partial fraction decomposition because I need it to be in this form. I need it to look like 1 over 1 minus y so that I know from yesterday this is going to be n equals 0 to infinity of y to the n. So I need to turn this rational function into two rational functions in which I can do this replacement to turn them into a series. So the first thing I'm going to do is write this as 5 over x minus 3 x plus 2. By partial fraction, this is going to be a over x minus 3 plus b over x plus 2. Now I'm going to do my partial fraction like I normally would do, so I'd multiply this by the lowest common denominator, and multiply this by the lowest common denominator, and I have 5 is equal to a x plus 2 plus b x minus 3. So 5 is equal to ax plus a 2a plus bx minus 3b. That means 0 is equal to a plus b by the fact that I have no x squared on the left-hand side. And 5 is equal to 2a minus 3b. From this first equation, I have a is equal to negative b. And the second equation, I have 5 is equal to 2a minus 3b. So 5 is equal to 2 times negative b minus 3b. So I end up with 5 is equal to negative 5b. B is equal to negative 1. A is equal to 1. So 5 over x squared minus x minus 6 becomes 1 over x minus 3 minus 1 over x plus 2. I am closer to having the form that I need for the replacement, whatever I see 1 over 1 minus y. So what I'm going to do is I'm going to divide everything by 3 first. And you're thinking, but wait a minute, did you say yesterday or 6.1 not to do that? Well, yes, if you have an x squared. But divided by a constant is not going to do anything other than get me the one that I need. So then this becomes 1/3 over x divided by 3 minus 1. It's getting closer. Do the same thing for the other one. So I have 1/2, the other term, x divided by 2 plus 1. If I factor a negative out of the denominator there, this will become negative 1/3, 1 over 1 minus x divided by 3. And then this one, I don't have to do anything like that, but I can factor out the 1/2, so I have 1 over. I'm going to write this as 1 minus an x, negative x over 2. Now, if I were to say let y equal x over 3, I can use that form. And if I say let y equal negative x over 2, I again can use that form. So this is then equal to negative 1/3, the summation of n equals 0 to infinity of x divided by 3 raised to the n. Simultaneously, I'm going to have minus 1/2, the summation of n equals 0 to infinity of negative x over 2 raised to the n. Like I did yesterday, I want to be able to bring in that constant, and I have a negative 1/3 and I have a negative 1/2. So I'm going to write this as negative n equals 0 to infinity of x to the n over 3 multiplied by 1 over 3. And that should be 3 to the n. I'm going to do something similar to this second one, but it's going to pull in a negative 1/2. Now, the reason I didn't pull in a negative 1/3 is because this isn't negative 1/3. This is a positive 1/3, but this, I can write this as a negative 1/2. N equals 0 to infinity of negative 1/2 raised to the n, x raised to the n, and then multiplied by a negative 1/2. because this term is now positive, I'm going to write it first for no other reason than I like to have it positive first. So I have the summation of n equals 0 to infinity of negative 1/2 raised to the n plus 1 x to the n minus the summation of n equals 0 to infinity of x. Actually, I'm going to write it as this way. I'm going to write it as 1 over 3 raised to the n plus 1 x to the n, which I can rewrite as n equals 0 to infinity of negative 1/2 n plus 1 minus 1/3 n plus 1 x to the n. Now, I brought it into as a single series. I didn't have to do that because I really wanted the radius of convergence. So I want the radius of convergence, and I would do my normal radius of convergence stuff, like my normal limit, the limit as n approaches infinity of a sub n plus 1 over a sub n, that kind of stuff. But what ends up happening is for this one, my radius of convergence, my first term here, my radius of convergence ends up becoming 2. Just like this one, the radius of convergence ends up becoming 3. Now, you should check this on your own. You shouldn't take my word for it. You really should check this as true. So by my theorem above, I'm going to take the one as the smaller radius of convergence, which is this one. Now, did they want me the interval? Nope, they just want the radius of convergence. So this is my answer. Now, let's look at these examples in which I'm asked to write each power series as a rational function. Couple of things to note. I need, for my ability to use n equals 0 to infinity of x to the n, so to be able to write the power series as a rational function, I needed to start at 0. My first example, and in fact my second example, does not start at 0. I needed to start at 0. So if I were to start writing this out, this would be 1 over x plus 1 over x squared plus 1 over x cubed, and etc. I need this to start at 0. So I need to adjust the index, and the way that I'm going to adjust the index so that I ensure that I put in 0, then I'm going to rewrite this as a summation of n equals 0 to infinity of 1 over x to the n. Now you're thinking, but that didn't change anything. Well, no. But now I'd have 1 plus 1 over x plus 1 over x cubed, and that's not what I want. I want to start with 1 over x. The way that I can ensure that is I write 1 over x in front. So then this 1 over x in front of all of my series will ensure that I now start with my index as being at 0, but I didn't change the series because I need it to be my ability to do this, right? I need it to look like that. So then this is going to be equal to 1 over x multiplied by, what we've been doing so far is we've been going in this direction. Now we're going to go in this direction. So the summation of n equals 0 to infinity can be replaced with 1 over 1 minus 1 over x. Multiplying everything by x, I have 1 over x. I have x over x minus 1. You can see that these x's cancel. And my final answer is 1 over x minus 1. And that's my final answer. My next example is similar. I need this to start at 0. So first what I'm going to do is to start writing out, what do I have? Just like I did before. So starting out with my first term, I have 1 over x minus 3, and then I have it to the 1 power. and then plus 1 over x minus 3. And then I'm going to have 2, 4, so that's 3. And then my next term is 1 over x minus 3 raised to, I put in 3, so I get 6, 5. And it continues. So now I'm going to rewrite this so that I can start at 0. Well, what does it do to my terms here? Well, n equals 1 to infinity. If I have 1 over x minus 3 raised to the 2n, what does that do? Well, I'm going to start this to 0. This is going to give me 1 over x minus 3 raised to the 0. That didn't help. 1 over x minus 3 raised to the 2. 1 over x minus 3 raised to the, so 0, and then 1 gives me 2, 2 gives me 4. Oh, to make this match, I just need 1 over x minus 3. So then if I multiply this by 1 over x minus 3, then when I distribute it through, I'm going to get the first term, I get the second term, and I'm going to get the third term. So then, this is my series. Now I can use this reversal and say, ooh, this is going to be equal to 1 over x minus 3 multiplied by 1 over 1 minus 1 over x minus 3, the quantity squared. So, as before, I need to deal with this complex fraction, just like I did with the complex fraction here, up above, not this one. So I need to multiply everything with every term within my complex fraction by x minus 3, the quantity squared. So 1 over x minus 3 multiplied by x minus 3, the quantity squared, over x minus 3, the quantity squared, minus 1. Now you can see that this cancels with one of those. So it gives me x minus 3. And then in the denominator, I have x minus 3, the quantity squared, minus 1. Which I'm totally fine if you leave it like that. But if you don't want to leave it like that, you can multiply the denominator out. And you're going to get x squared minus 6x plus 8. So this is equivalent to my series I started out with, which was n equals 1 to infinity of x minus 3, 1 over, and then 2n minus 1. All right, for this example, what we're going to do is, once again, we're going to break it apart into the two pieces. So this is going to be equal to the summation of n equals 1 to infinity of 1 over x minus 3 raised to the 2n minus 1 minus the summation of n equals 1 to infinity of 1 over x minus 2 raised to the 2n minus 1. And as before, I would start writing these out so I can get a feel for the adjustment that needs to be made. And I'll let you do that. I'm going to jump right to what I need. This is going to be 1 over x minus 3, the summation of n equals 0 to infinity, of 1 over x minus 3 raised to the 2n, minus 1 over x minus 2, the summation of n equals 0 to infinity, of 1 over x minus 2, the 2n. This then becomes 1 over x minus 3, 1 over 1 minus 1 over x minus 3, the quantity squared, minus 1 over x minus 2, multiplied by 1 over, 1 minus 1 over, red rover, send 1 over. Anyways, when I get totally done, my final answer is going to be x squared minus 5x plus 7 over x to the 4th minus 10x to the 3rd plus 35x squared minus 50x plus 24. Now, I just want to let you know, I am a fan of not multiplying the denominators, leave it in factored form. But you do need to make these two fractions here into a single fraction. And the numerator does need to be simplified, but the denominator does not. So if you don't want to simplify the denominator by multiplying stuff through, leave it in factored form. It's actually preferable that way. Here's an example where we have a real-life application. We're going to calculate the present value of P of the annuity in which $10,000 is to be paid out annually for the period of 20 years, assuming the interest rates of R equals 0.03, R equals 0.05, and R equals 0.07. So 3%, 5%, and 7%. Now, we have the formula in our book for the annuity. The formula in our book is P is equal to the summation of n equals 1 to n. In this case, we're going to go to 20 years, so this is 20. And it's going to be C over, and then I have 1 plus R raised to the n. So that is from the book. Our first one for P sub 1 is going to be equal to the summation of n equals 1 to 20, not to infinity, because you're only going to do it for 20 years. We're trying to figure out what the principal amount would be to have this happen. So this is going to be my 10,000, that's my C, over 1 plus my rate, which is 0.03, raised to the n. Now, if I were to write this thing out, it would be 1 over 1.03 plus 1 over, and you think, where did the 10,000? Well, I'm going to leave my 10,000 out front because I just don't want to keep writing it. No, I think I got one too many zeros. Yep, I got one too many zeros. No, I don't. Okay. Anyways, and then it's going to be 1.03, the quantity squared, plus ... 1 over 1.03 raised to the 20, which is equivalent to 1,000. And I end up with 1 over 1.03, 1 minus 1 over 1.03 raised to the 20 over 1 minus 1 over 1.03. And my final answer, if I want to have $10,000 a year for 20 years, I need to have an initial investment of 148,774.70. So that's how much money I need to invest to begin with. Now, for the annuity at 5%, if it's at 5%, P sub 2, which is at 5%, this ends up being $124,622. And P of 3 at the 7%. This is going to give me, the amount is 105,940.10, 10 cents. So here's an application for taking my power series and turning it into a rational function and being able to calculate something fairly quickly. Now, we're going to take the time to take a polynomial and write it as a power series. As I look at my first one, I'm going to lump together the negatives and I'm going to lump together the positives. And the reason I'm going to do that is because it's not alternating. It's a positive, positive, minus, minus, positive, positive, minus, minus. So let me put them together based on the sign in the front. So I start out with x plus x squared plus x to the 5th plus x to the 6th plus ... and then minus x to the third, minus x to the fourth, minus x to the seventh, minus x to the eighth, minus dot, dot, dot. So I'm trying to find a pattern here. Well, from 1 to 2 is a difference of 1. From 2 to 5 is a difference of 3. From 5 to 6 is a difference of 1. But I have x plus x to the fifth. The powers there have a difference of 4. Ooh. Plus dot, 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 plus x squared plus x to the sixth plus dot, dot, dot. Now those powers have difference of 4s between them. So then let's look at the negatives. I'm going to do the same thing. So I have negative x to the third minus x to the seventh minus dot, dot, dot. Those have a power difference of 4. And then minus x to the fourth minus x to the eighth minus dot, dot, dot. Those have a difference of 4. Because these have a difference of 4, then this I can write as the summation of n equals 0 to infinity of x raised to the n plus 1, so 4n, because there's a difference of 4, so 4n plus 1. That's that part of it. Let's just check it. If I put in 0, I get 1, cool. If I put in 1, I get 5, cool. That seems to be working. This one is going to be slightly different. It's still going to be the summation of n equals 0 to infinity. Now, I notice that there's a difference of 4n between them. So it's still going to be x raised to the 4n, but I start at 2 instead of 1. And you're right. This is going to be minus the summation of n equals 0 to infinity of x raised to the 4n plus 3. You are correct. And if you're thinking the next one, clearly must be a negative summation of n equals 0 to infinity of x to the 4n plus 4, you are correct. Now, what I want to do is be able to add these together. For me to be able to add these together, I need to have the same summation. I need x raised to the 4n. So, and this is a plus between them, I'm going to rewrite this as x. Let me actually give you some more steps. The summation of n equals 0 to infinity of x to the 4n multiplied by x. Now the x now is not dependent on n, so I can take this x out front. So I can write this as x out front, and it won't have it inside anymore. And if you're thinking I'm going to do that to all of them, you are correct. So then plus x squared, the summation of n equals 0 to infinity of x to the 4n, and then minus x to the third, summation of n equals 0 to infinity of x to the 4n, and then minus x to the fourth, summation of n equals 0 to infinity of x to the 4n. Now each one of these has the summation of n equals 0 to infinity of x to the 4n. So I can factor that out, leaving me x plus x squared minus x cubed minus x to the fourth multiplied by the summation of n equals 0 to infinity of x raised to the 4n. Now, using the fact that I have 1 over 1 minus y, this is equal to the summation of n equals 0 to infinity of y to the n. And if you're thinking my y is going to be x to the fourth, you are correct. So this is going to be equal to x plus x squared minus x to the third minus x to the fourth over 1 minus x to the fourth. And you can totally leave it like that. You can, however, if you like to have your leading coefficient positive and have it in descending order, you would pull a negative out of this denominator, which would make this now x to the fourth minus 1, which would then bring that negative up into the numerator, which would give me a negative, negative, or this becomes positive, positive, negative, negative. It's totally fine to do. I'm actually fine if you leave it right here. But if you choose to do that, then your final answer would be x to the fourth plus x to the third minus x squared minus x all over x to the fourth minus 1. And that's your final answer. Let's take a look at my next example here. So again, what I'm going to do is see if I can do grouping. Now, this, once again, does not have a plus, minus, plus, minus. It's plus, plus, minus, plus, plus, minus. So, if I start with x over 2 plus x squared over 2 squared, because that's what 4 is, plus x to the 4th over 2 to the 4th, plus x to the 5th over 2 to the 5th, plus dot, 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 minus x to the 3rd, 2 to the 3rd, minus x to the 6th, 2 to the 6th, minus dot, dot, dot. Now we can see that these have a difference of 3. So if I'm just looking at from 3 to 6, that's a difference of 3. So I need to make these to have difference of 3. So I'm going to group these two, and I'm going to group these two. So I have x over 2 plus x to the 4th over 2 to the 4th, dot, 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 plus x squared over 2 squared plus x to the 5th over 2 to the 5th plus dot, 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 minus x to the 3rd over 2 to the 3rd minus x to the 6th over 2 to the 6th. Now, you're going to be so surprised that I'm going to write this as the summation of n equals 0 to infinity of x over 2 raised to the 3n, because that was a difference, plus 1, plus the summation of n equals 0 to infinity of x over 2, 3n plus 2, minus the summation of n equals 0 to infinity of x over 2 raised to the 3n. As before, I'm going to factor out an x over 2, n equals 0 to infinity of x over 2 raised to the 3n, plus x over 2 squared, summation of n equals 0 to infinity of x over 2 raised to the 3n, minus, and then I have nothing to pull out of this last series, x over 2 raised to the 3n. Factoring out this, and this, x over 2 plus x squared over 4 minus 1, summation of n equals 0 to infinity of x over 2 raised to the 3n. And if you're thinking, I got a nice replacement for that, you would be correct. I do, however, need to make my fractions all the same. So, making my fractions all the same. Oh, because I'm starting at 0, darn it, I need to make sure I have a plus 3 there. I just got so excited, I thought I didn't need anything, but I do because I'm starting at 0, not 1. I need to have this x to the 3 divided by 3, or x to the 2 divided by 3. I was just so excited. I need to erase this. X to the 3rd divided by 8. I was just so excited. Anyways, multiplying everything by 8, I'm going to have 8x. Excuse me, not everything by 8. Multiplying everything to make sure that we have a common denominator of 8. This is going to be 4x plus 2x squared minus x to the 3rd all over 8. And then we know that this can be replaced with 1 over 1 minus x divided by 2 raised to the 3rd power. When I finally get done with all of this, I'm going to end up with simplification x to the 3rd minus 2x squared minus 4x all over x cubed minus 8. And that is my final answer there. Now we're going to look at the multiplication of a power series. We've done addition and subtraction of power series. What happens if I multiply two power series? All right, so suppose I have these two power series where I have different coefficients. We both start at n equals 0 to infinity, still x to the n on both of these. If they both converge, if f and g converge respectively on a common interval of I, then my coefficient e sub n is going to be equal to c naught dn, c1 d to the n minus 1, c2 to the d n minus 2, all the way down to where we get cn d naught. So in other words, the very first coefficient on my c on my first series will be multiplied by the last coefficient on my D. When I get down to the end, it'll be my last coefficient on my C is going to be multiplied by the first coefficient on my D. If that's true, then we end up with the multiplication is going to be n equals 0 to infinity of e sub n x to the n, and it will converge on the multiplication of these two. Let's take a look at an example. I don't know why that unlocked there. If you all know why that always unlocks the rotation, would you just let me know? Because I don't know why it does it. It just drives me batshit crazy. I know it probably shouldn't, but whatever. Okay, so we're going to find the Cauchy product of this and from the theorem above. First thing I'm going to do is I'm going to rewrite my f of x as a summation of n equals 0 to infinity of 2x to the n. And my g of x is fine. Now my a sub n is going to be 2. My b sub n is going to be n. So using the formula above, my e sub n, my Cauchy product, is going to be the summation of k equals 0 to n of c sub k d to the n minus k. So now I'm going to decide which is going to be the easiest d sub k minus n, which is going to be the easiest k. Well, if I look at my a sub n, it's going to be the same no matter what, right? No matter what I'm doing, it's going to be the same. So this is going to be 2. I'm going to choose that one to be the d sub k. And then that means my c sub k is just going to be n. So this is going to be the summation of k equals 0 to infinity of 2 to the n. I can rewrite this as 2 because it's a constant. I can pull it out of n. I'm going to go and run out to my pre-calculus 2 book, and I have, it shouldn't be to infinity, it should be to n. Because my Cauchy says it should go to n, and I'm using this, by the way, n and n. Go out to my pre-calculus 2 book, and I have a summation for this type of series. It ends up becoming, if I have the summation of k equals 1 to n of n, this is going to be equal to n plus 1 multiplied by n divided by 2. Now the fact that I start at 0 doesn't do anything for me. I can start at 1 because it just means the first term is 0. So this will be equal to 2 times n plus 1 divided by 2, which gives me n plus 1. Now that I found that coefficient, right, I found my coefficient here, my e sub n. I can say the multiplication of 2, the summation of n equals 0 to infinity of x to the n, multiplied by the summation of n equals 0 to infinity of n x to the n will become, those two cancels, the summation of n equals 0 to infinity of my e sub n, which is n plus 1, multiplied by x to the n. And that's what you end up with. Let's take a look at my next example here. And the first thing I'm going to want to do is find my Cauchy product, my e sub n. My a sub n is going to be, well, let me rewrite this as the summation of n equals 1 to infinity of x as 1 over 2 raised to the n, x to the n, so I can see my coefficient a little bit better. My a sub n is going to be 1/2 raised to the n, and my b sub n is also going to be 1/2 to the n. My Cauchy product, e to the n, is going to be, again, my formula is the summation of k equals 0 to n, not infinity, k equals 0 to n of c sub k d sub n minus k, which is going to be the summation of k equals 0 to n of 1/2 raised to the k, 1/2 raised to the k minus 1. I mean, n minus k. N minus k. N minus k. Now this is equal to k equals 0 to n. Because my bases are the same, I add my exponents and I just get 1/2 raised to the n. This ends up becoming, again, I'm going to go pull out my Pre-Calculus 1 book, and I have a fact that this is a geometric sequence, and so we know that this is going to sum up to, my r happens to be 1/2, and so this is going to sum up to n over 2 raised to the n. So that's what that sums up to. So then this multiplication is simply going to be the summation of n equals 1 to infinity of n over 2 to the n, x raised to the n. And I can leave it like that, or if I'm inclined, I could write this as n equals 1 to infinity of n and then x over 2 raised to the n. I'm actually okay with either one of them. Now let's look at differentiating and integrating power series. So if we have a polynomial with a finite number of terms, we can do the derivative all day long. And we do it term by term. And we can evaluate the indefinite integral by integrating each term one by one. So a term by term in differentiation and integration of power series. Suppose I have this power series where I have a center, and I'm just center of a rather than 0, but if it's 0, it's still okay. Then it will converge on this interval from a minus r and a plus r for some r greater than 0. Let the function f of x equal this, which we know expands to this. For a, the absolute value of a less than, absolute value of x minus a less than r, then f is differentiable on this interval, which means we can differentiate this term by term. So if I expand this out, the differentiation of c naught goes to 0, then it's just going to be c sub 1. And then this, by the chain rule, it's going to be 2 c sub 2 a x minus a. This 3 will come down, so 3 c sub 3 x minus a, the quantity squared, and etc. Etc., etc., etc. And it did it again. This continues, of course, and I can integrate it. So the integration of f of x dx is going to be c, some constant of integration. You can put it first or last, plus the integration of n equals 0 to, or plus the summation of n equals 0 to infinity of c sub n, x to the n minus a, n plus 1 over n plus 1. So that's just reversing the power rule. Differentiate the given series expansion of f term by term to obtain the corresponding series expansion for the derivative. Okay, so the first thing I'm going to do is focus in on this side. So if f of x is equal to 1 over 1 minus x squared, we know that this is equal to the summation of n equals 0 to infinity of x raised to the 2n. So if I do d dx of 1 over 1 minus x squared, then I would do d dx of the summation of n equals 0 to infinity of x raised to the 2n. This right-hand side, using the theorem up above, that part, is going to give me the summation of n equals 0 to infinity of 2n, that's bringing the power down out front, x raised to the 2n minus 1, which is equal to, I put in 0, I'm going to get 0, plus I put in 1, I'm going to get 2x. I put in 2, I'm going to get 4x to the third. I put in 3, I'm going to get 6x to the fifth. I put in one more, I'm going to get 8x to the seventh. Now I can see what this is going to be equal to. If I factor a 2 out, then I'm left with x plus 2x to the third plus 3x to the fifth plus 4x to the seventh plus dot, dot, dot. And then it just makes it easier to see that I have this series, which will become the summation. The summation of n equals 0. 2 is going to be out front to infinity. Now I need to make sure that when I put in 0, I get x. When I put in 1, I get 2x to the third. So I know my x needs to be 2x plus 1 because I'm going up by 1, 3, 5, 7, so that's the 2n. I need to start with 1, so that's where the 1 comes from. So that gives me x raised to the 1 in the first position. Now what I also need is I need it so it is not 0 for the first term. So when I put in 0, I better not get 0. I need to have a 1 right here. So the way that I can make sure I get a 1 right there is I put in plus 1. So when I put in 0, I get 1. When I put in 1, I get 2. When I put in 3, I get 4. So what I'm doing is I'm breaking this down into 2 arithmetic sequences. The first arithmetic series is 1, 2, 3, 4, and so I'm looking at the coefficients. This gives me the coefficients. The next thing I'm looking at is the power, so 1, 3, 5, 7. This is the arithmetic sequence for the powers. And then I just need to make sure that I start out with the 2 out front. This 2 here is still this 2. All right, let's take a look at the next example. We're going to integrate the series expansion term by term from 0 to obtain the corresponding series expansion for the indefinite integration. So the first one I did the derivative. Now I'm going to do the integral. So I know that f of x is equal to 2x over 1 plus x squared, which is equal to 2 times the summation of n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1. So let's start expanding this. So I'm going to have this 2 out front. I put in 0, I'm going to get negative 1 to the 0, which is 1, and then I'm going to just get x. And then I put in 1, and I'm going to get negative 1, so negative x raised to the 3. And then I'm going to put in 2, and I've got a positive again, and that's 4x to the 5th. I'm going to put in 3, so it's going to be negative again, x raised to the 7th, and then dot, dot, dot. Now I'm going to actually integrate it term by term. So the integration of f of x is going to be the integration of 2x from 0 to x dx minus 2, the integration from 0 to x of x cubed, plus 2, the integration from 0 to x of x to the 5th dx. They should all have a dx. Plus dot, dot, dot. You kind of get the idea. So this ends up becoming x squared. This is going to be minus x to the 4th divided by 2. This is going to be plus x to the 6th divided by 3. And the next one I'll just put in there is x to the 8th divided by 4 plus dot, dot, dot. You kind of get the idea from there. I'm going to write this over 1. And so writing the series, this represents as n equals 0 to infinity. I'm going to have negative 1 to the n because it's alternating. My x's are going up by 2's, and I have to ensure that I start out with something other than 0. X to the 0, that is. So it's 2n plus 1. That's going to ensure that I start out with, and that should be 2 plus 2. That'll ensure that I start out with x squared, and then x to the 4th, and x to the 6th. In my denominator, I have n plus 1. So that is what my integration ends up being. Now, if I were to actually integrate 2x over 1 plus x squared dx with a u sub, this ends up becoming the natural log of the absolute value of 1 plus x squared. So then this is the equivalence of what the natural log of 1 plus x squared would be in terms of a series. My next example, I'm going to evaluate each indefinite series by identifying it as a value of a derivative or an integral of a geometric series. So first thing I'm going to do is look at what I've got and what's given to me. So they're giving me f prime of f is equal to 1/2. So because of this, I think I'm going to start out with the derivative of f. So d dx of f of x, which is the d dx of the summation of n equals 0 to infinity of x to the n, which is going to give me the summation of n equals 0 to infinity of n x raised to the n minus 1. At the same time, though, the summation of n equals 0 to infinity of x to the n is going to be 1 over 1 minus x. So that's also equal to f of x. So f prime of x is equal to, by the chain rule, negative 1 minus x, the quantity squared, multiplied by negative 1, which gives me 1 over 1 minus x squared, 1 minus x, the quantity squared. F prime of 1/2 is going to give me 1 over 1 minus 1/2, the quantity squared, which is 1 over 1 over 4, which gives me 4. But if I have this as f prime of 1/2, then this also equals the summation of n equals 0 to infinity of n 1 over 1/2 raised to the n minus 1, which is going to give me the summation of n equals 0 to infinity of n, and then I'm going to write this as 1/2 n 1 over 2 raised to the negative n, which 1 over 2 raised to the negative n is going to give me 2. So this is 2 the series of n equals 0 to infinity of n 1 over 2 raised to the n. But these two things have to be equal. So these two have to be equal. So 4 has to equal 2, the summation of n equals 0 to infinity of n 1/2 raised to the n. Dividing both sides by 2, I get 2 is equal to the summation of n equals 0 to infinity of n 1/2 to the n, or I can rewrite it as 2 is equal to the summation of n equals 0 to infinity of n over 2 to the n, which is what I was asked to evaluate with, given this other information. So my answer is 2. So there's my answer. And I'm done.